Another integration technique works well with rational functions, and this technique is called partial fractions. So let's take a look using a rational function. In this case, 5x plus 5 divided by x minus 1 times x plus 4. And this rational function can be rewritten as the sum of two fractions. And this is the basic idea behind partial fractions. And in this case, that is 2 over x minus 1 plus 3 over x plus 4. And in this way, these rational functions can just be kind of decomposed into two parts. And of course, this is really useful for when we're finding the integral of the original function. And we know that it's got an equivalency of two fractions, or two smaller ones, because now I can take the integral of each piece and it will work out. So the question is, how do we go from this function to having these two functions? And that's the tricky part. So let's take a look at that through another example. And so here we have the integral of x dx over x squared minus 5x plus 6. Again, we have a rational function. First step to trying to pull this apart is to factor the denominator. And then the second part is to realize that this is going to split up. This is going to be two parts. One part is going to have a denominator of x minus 3. I don't know what that is, so I'll call it a. And there'll be another piece that will have that denominator of x minus 2. And the trick is I need to try to find a and b such that it equals the original function. So the original function looks like this, and I want part of it to be over 3 and another part of it to be over 2. And now the trick is to solve for a and b. And we do that by finding common factors, a common denominator between these. So once they all three of these pieces have a common factor, this a part is going to get multiplied by x minus 2. The b part is going to be multiplied by x minus 3. This becomes ax minus 2a plus bx minus 3b. And so pulling together the x terms, a plus b will be the coefficient for x, and minus 2a minus 3b will be left over. And what we have now is a system of equations. We know that the coefficient for this x is 1, so 1 will have to be a plus b. And then we know that this piece here, minus 2a minus 3b, will have to be equal to 0. And we can solve this system of equations in quite a few different ways. The easiest is probably some sort of a substitution. Maybe a is equal to 1 minus b, and put that in here. Negative 2, 1 minus b minus 3b is 0. And I'm just solving this gives negative 2 plus 2b minus 3b equals 0, or negative b equals positive 2, so b is negative 2, and therefore a, substituting it back in, a is 1 minus negative 2, so a is 3. And so now I have 3 over x minus 3 dx plus negative 2 over x minus 2 dx being equivalent to x dx over x squared minus 5x plus 6. And so now we can go and solve this with some simple substitutions. Let's take a look at another example. Okay, so here's the next example, and what I want to do with this one is find the equivalent fractions of x squared plus 2 over all three of these binomials and split this into three pieces. One that's over x minus 1, I'll call that a. Another one that's over 2x minus 8, I'll call that b. and another one that's over x plus 2, I'll call that c. And so we have to think about what does the first term need to be multiplied by to allow it to be equivalent. And so the a value is going to get multiplied by 2x minus 8 and x plus 2 to have a common denominator. And we're going to have a b value that gets multiplied by x minus 1 and x plus 2. And we're going to have a c value that gets multiplied by x minus 1 and 2x minus 8. And all of this together is going to be equivalent to our x squared plus 2. So we need to expand and simplify this and make it equivalent. So I will do that next. So here's the expansion, and now I want to collect the x squared terms so that I can compare them, and so I get 2a, so x squared has a 2a term plus a b term plus a 2c term. The next is the x's, and there are none. There are no terms. Oh, sorry, there are. There's negative 4a x. There's plus 1bx and minus 10cx. And then the just regular number terms are negative 16a and negative 2b's and 8c's. And so this first piece has to equal 1. So 2a plus b plus 2c's will be 1. And this second part, well, there's no x's, so this part has to equal 0. Minus 10c, that part will be 0. And then this last piece has to equal positive 2, so negative 16a minus 2b plus 8c will be 2. And so now I have 3 equations and 3 unknowns. I can go ahead and solve this system. Solving this system will give you a equals negative 1/6, b equals 1, and c equals 1/6, and thus allowing you to write out your partial fractions where the original rational number, rational equation, 2x minus 8 over x plus 2 can be put into 3 parts. One with the a value of negative 1/6 over x minus 1, second with the b value of 1 over 2x minus 8, and the third piece with the integral of 1/6 over x plus 2, for which we can quite easily integrate each of these pieces to get a final solution, as shown. And that's all. Okay, let's take a look at one more example. What happens if we have a rational expression, rational function, where the numerator is bigger than the denominator? Sometimes we can use long division to help break this apart and make it into the partial fractions form. And so we set up the long division to see how many times x squared minus 4 can go into the numerator, remembering the 0x squared and 0x. I'll perform those calculations now. And interpret this as a result of it goes in x times, and then the remainder is based on what's left over here over the number that we're dividing in by. So I get a remainder of 4x plus 1 over x squared. And so I can rewrite this integral in parts. There's one part that is kind of the whole number of times that x squared minus 4 went into the numerator, and then I'm left over with this partial fraction, which I'm going to need to use some of the techniques discussed earlier, so I will factor right away this into x plus 2, x minus 2. The first integral becomes x squared over 2, and the second integral breaks into two pieces. So we get the integral of a over x minus 2 dx and the integral of b over x plus 2 dx using the partial fractions that I have shown you before. And then we can create our system. So we can create a system from this and solve to get a as 9 over 4 and b as 7 over 4. Substitute those back in and make some final simplifications to this. So I get as a final answer x squared over 2 plus 9 over 4 ln absolute x minus 2 plus 7 over 4 ln absolute x plus 2, and then don't forget the c, and that should be x plus 2. Not sure why it's not showing up.